Welcome to Motion Talks, an ABB podcast created to encourage open conversation about what's driving change across industries and infrastructure. Hear from industry experts and thought leaders as we talk about the technological innovations and trends impacting these spaces. Want to learn what's shaping their sustainable transformation and growth? Then this is the place for you. I'm your host, Natalie from ABB in Australia, and I hope you enjoy this episode. I'm really looking forward to today's topic. My guest is Tony Morton, an electrical engineer who has worked to improve the performance of power systems, large and small, for over 20 years. He's done academic work in the control of DC microgrids and on improving the operation of distribution networks in remote rural areas. He's also spent the past 15 years as a consultant to the grid scale renewable energy industry worldwide. Tony is currently a principal power systems engineer and global technical head at Vysus Group, a leading engineering and technical consultancy offering specialist asset performance, risk management, and project management expertise across complex industrial assets and energy assets, including renewables. Tony, welcome to Motion Talks.
Thank you very much, Natalie.
So, Tony, today we're going to talk about something at the forefront of Australian news at the moment, and that is the country's transition to renewable energy. So, renewable energy capacity in Australia is expected to double or even triple over the next 20 years. And if we look at the state of Victoria alone, we're experiencing an influx of new wind and solar farms after a staggering fourfold increase in applications for generation licenses since 2017. Can you tell us a little bit about your work in this space and why you think the energy sector has gained so many pipeline projects in recent years?
Well, thanks. I think it's interesting to look back really to when my early days in the industry, back around the turn of the century, 20 years ago, when really you would say there was next to no grid scale renewable energy in Australia's electricity network, and we've gone from that to having I think about 25% of our energy now is supplied from renewable energy, largely wind and solar energy, and that has really the largest part of that has actually occurred within the last 10 years, particularly with the massive solar boom that we've seen since 2010. And it's been both in the large-scale wind farm and solar farm developments up to hundreds of megawatts on these very large sites around Australia, but also just people putting solar panels on their rooftops, and that is it's definitely a non-trivial proportion of that. It's you look at South Australia, for example, and what you find is that there are times there when nearly half of all the electricity in the grid is actually being supplied by rooftop PV systems, and this is a really interesting development and a really interesting challenge for the electricity industry. Because I like to say that the one thing that's really challenging and also quite exciting for us as engineers is that it's not only a transition that we're seeing in energy sources, which is really necessary to help us combat climate change and to deal with the carbon emissions problem we have around the world, but it's also an equally big transition in technology.
So I guess that leads into my next question. Where will all these renewable energy technologies be built and how will it actually work?
And that's another really interesting aspect of this. That a big challenge for the industry has been the fact that we no longer build our electricity network based on so much on the idea of big generation centres and big load centres. The old paradigm of big centralised generators that were concentrated in particular geographic locations really no longer holds. We are seeing the wind and solar farm developments basically chase the resource to where it's to where that is best, and trying to make that work with a grid that historically was not designed with generation at these different locations in mind. It was very much designed, most of it about a century ago, for the purpose that applied at the time, which was simply to feed electricity from big thermal power stations in coal-rich and hydro-rich regions in Australia, like the Latrobe Valley, the Hunter, and central Queensland, to the capital cities where most of the load was, and so we still have transmission networks that are optimised for that particular task, which is declining in relevance as we see that not only is generation spreading to be literally all over the map, but the demand on our power system, the patterns of that are changing as well, so that the whole profile of how power flows around our electricity system is very different, and that creates a lot of challenges for the industry as we try and adapt and optimise the connections of all of these new wind and solar and storage developments, to really to reverse engineer those almost onto a transmission system that was built for quite a different purpose, and which now has to be re-optimised for this new purpose, but doing it in a most cost-effective manner, because we run an electricity market in Australia notionally on the idea that energy should always be supplied and developed in a way that exposes consumers to the least possible cost, and that means the least possible new investment in our transmission network as well, which does raise a lot of challenges.
Yeah, and on that topic of challenges, one of the biggest challenges for new projects in Australia, in terms of what we've already seen, is what's called low system strength. So, what does that actually mean? What would you say about what that means, and why do you think it's such a concern?
So this again comes to the question of how we can optimise grid connections of big energy developments in sections of the network that didn't have big energy developments in mind. So Australia has what's often called a very long, stringy network, because it was based on just moving power mainly from the big coal centres to the capital cities, and then a much smaller network in terms of the asset volumes to get it around to all the regional and rural areas. We're now seeing it's those regional and rural areas that are the focus for a lot of generation development. And system strength is this technical concept that we engineers have, which basically comes down to the effective electrical distance between 2 points in a network. Basically, if you have a big thick piece of wire between 2 points, like a great big pipe, then it's a lot easier to coordinate the voltage and power flow between those points, and everything's a lot more stable than if you have a very thin wire or a thin pipe connecting those same points. What tends to happen in that case is there's a lot more sensitivity the basic electrical quantities, all of these numbers that measure how the system is the health of the system and how it's working at transmitting power from one place to another, the voltages and currents and power flows and so on, they're all so much more sensitive and more inclined to wobble in response to small disturbances. That's what we call low system strength, when you have that high sensitivity and that greater inclination. If you like, it's like having a stiff spring versus a very pliable string. One tends to result in a lot more bounce than the other. So it's that bouncing around that we have to try and control and keep under control in order to make sure everything hangs together and the lights stay on.
Absolutely. It's a good way of putting it into perspective, that visual way of seeing what's actually going on. And so, Tony, you raised the point that renewable electricity isn't just an energy transition, but also a technology transition. Can you tell us a little more about what you mean by this?
So the way that we've traditionally designed big alternating current power systems is, and in particular the generators in those systems, the devices that take the original power, which traditionally was big hydro water flows down hills, or it was big coal boilers and gas boilers and so on, and converting that into electricity. The thing that we used for that was what we call the synchronous electrical machine. So it is the workhorse of the traditional large power system. Every large generator in the system historically has been one of these synchronous machines, which is a big piece of spinning iron, essentially, that has a mechanical input which comes from a turbine, which comes from the prime energy source, and it spins at very high speed, and it's basically a set of magnets inside it which induce production of electrical power from that mechanical energy source. And that is how we have produced almost all of our electricity for almost all of the 20th century. And these are very good electrical devices. The electrical machines, synchronous machines in particular, are very well understood. We know how to operate them with one another, so they all stay in sync and stable, and form the basis of very large power systems like the one in Australia. And in fact, it's been useful through the whole 20th century to picture the electrical power system itself as one great big synchronous machine made up of smaller synchronous machines. And it's been a very useful metaphor for thinking technically about the performance of the power system. But the technology transition we have it's based on the nature of new renewable energy sources. The fact that they're no longer just a big boiler that's providing a constant energy source into a turbine, or a falling stream of water that again is able to drive a turbine at constant speed. When we look at wind power, it's a variable speed source, as well as being just variable with the weather. It's also variable in the optimal speed of the turbine that we use to collect it. So the turbine has to be able to operate at high and low speed depending on the wind source. Solar energy is a static source, so there's no moving parts in a solar generator. So again, there's no machine to talk about. There's no mechanical stage. So what we are looking at increasingly is, instead of the grid being a big machine, it's actually more like a big electronic appliance, much like the appliances in our house. They're much less based on big heavy iron and moving parts, and more based on little electronics, or in our case, it's bigger electronics, but it's still a very technically different kind of way of producing electricity and controlling the grid, because we can no longer rely on the mechanical characteristics of these big pieces of spinning iron to keep the grid in sync. We have to do it in other ways, and through even virtual machine technology is what we're thinking about during this transition to make everything work properly.
Yeah, it's like electronics on a much grander scale, isn't it?
That's really it. Yes.
Yeah. And you talked about power, Tony. So, power quality is also a significant challenge that relates to this new technology. So what are the main issues that you can think of, and what can be done to actually address them?
So the again with the technology transition, because we're using electronics, which are based fundamentally on switching things on and off very fast, instead of having this big rotating magnet which produces this nice smooth waveform of voltage and current. So when you're switching things on and off very fast to control them, you get a very fine degree of control and you get a lot of advantages from that. But the disadvantage is that the shape of the voltage or current that you're putting into the system is different. It's not necessarily that same smooth shape initially. It's got a lot of what we call harmonic distortion in it, and if we're not careful, it can also have what we call flicker distortion, because magnitudes are going up and down and so on. So this is what we call power quality disturbances, and there's a lot of clever technology around filtering and around compensation to take that noisy waveform that we get from the raw electronics and filter it out so that it's a nice smooth voltage and current that goes into the power system, and that other devices on the power system can tolerate a lot more easily. But of course, even the generators themselves, they're producing current and power in all of these weird and wonderful shapes and sizes, but they also need to be able much more to tolerate some of the noise and the distortion that's coming through from other things on the system. There's part of the evolution to being an electronic appliance is that things can get a little rough around the edges sometimes, and we both need to be working on reducing that roughness, but also tolerating it more in the devices that we have. And the devices we have these days in the 21st century are better at tolerating a lot of this noise, but there are limits to all of this, of course.
Yeah, absolutely. And that harmonic distortion is a whole nother subject in itself, isn't it?
It is, and it's one of the things that keeps engineers awake at night. Just thinking about all the ramifications, because it's very difficult. It's not only a big practical problem, but theoretically it's very difficult to really pin down. Understanding harmonics precisely in a power system for various technical reasons is comparable to nailing jelly to a wall. It's something that's extremely sensitive.
Yes.
So it's a real challenge for us to study.
Especially with that analogy, it almost seems impossible, doesn't it? And can you tell us a little bit more about some of the consultancy services Vysus Group provides to help with a vital topic that we've addressed today, which is that ensuring a smooth transition to renewable energy as a power source and that effective project execution?
Yes, thank you, Natalie. I work for Vysus Group, which is a consulting team based in Australia, although we work worldwide with most of our current work is involved in generator connections in the renewable energy sector. We work a lot with developers of wind and solar farms, and also with suppliers and OEMs in those industries and in the power system equipment industry, to really make sure that this transition is well managed from a technical point of view. So what we aim to do is bring all parties together in these technical negotiations and the analysis and studies required for understanding the performance of a new connection, and make sure that there's an outcome from that is satisfactory to everyone, but also satisfies the ultimate criteria of good practice, which is around cost effectiveness. It's around timely delivery. It's around being able to have certainty around the development of this increasing number of projects, which are which are coming in nearly on top of each other in some cases, and looking to make optimum use of that network that we have, while that network itself is slowly being upgraded to be fit to take more connections. We're trying to get as much as we can out of the existing network and do that while ensuring that everything operates correctly, the lights stay on, and the operators of that network can also be reassured that everything is performing as it should.
And it does become absolutely essential, doesn't it? Because it is such a huge investment, and you want to know that you're getting the best consultancy service for the project.
That's right. So, the team I'm with has been working in Australia for the last 15 years. We were in close to the start of the large grid scale developments initially in the wind industry back in the mid 2000s, and we've come right through with this transition to the boom in renewable energy developments, which is going to continue and keep growing. There's so much momentum behind the developments in the market, and we want to go with the market and ensure that everything can continue to be developed in a technically appropriate way, and in a way that makes sense commercially for those who are risking their own capital to make these things happen.
We've talked a lot about the rise of renewables in Australia and some of those frequent challenges that you've been helping your clients to address in your work. But can you talk to us about some of the technologies that you've seen that have been helping developers to avoid these issues upfront, but then also, I guess, long term?
So when we look in particular at something like system strength remediation, or when we look at power quality issues, there are various solutions available, and it really depends on some of the details of the technology that's going in, because not every wind farm is the same, not every solar farm is the same, just from a technological point of view, and from the point of view of the connection location. So in some cases we do look at, particularly in the interest of timely developments, to possibly looking at additional equipment. So there are a number of projects that are looking at things like synchronous condensers, which are they're kind of thought as a drop-in solution for some of these system strength issues. Essentially because we understand, we have a whole century of experience with rotating machines as the basis of grid stability. So it's a well understood solution to basically put in a rotating machine to supplement the electronics that's going in for the wind or solar farm. But of course, it's not the only solution. So ultimately, what we'll see with this transition is that the electronics themselves will evolve, and we are seeing them evolve, and we're seeing novel solutions with things like control system tuning, and also with the category of grid forming inverters, which are a type of electronic solution that essentially gives you some of the characteristics of those rotating machines, to ultimately be able to build a grid and rely on a grid that is based on these new renewable energy developments that are taking on all of the technical services and all of the technical characteristics that we have historically relied on as being supplied by these big thermal power stations with their synchronous machines. So there's lots of other things can be part of that. We have StatCom equipment for voltage control. We have active and passive harmonic filters to deal with a lot of those power quality problems. There are various equipment solutions that can be brought to bear on these problems, but also just the evolution of the technology and expertise in understanding how to optimally design and tune the control systems within the wind and solar plants themselves to behave in the way that's required. And we've made a lot of progress with this control system tuning to make everything work well, even to the extent that sometimes it's not necessary to look at this additional equipment, but it really depends on the project.
Yeah, absolutely. And I think you hit the nail on the head there where you mentioned the evolution of technologies, especially as you mentioned the synchronous condenser units. It's almost like a new take on an older technology, and it's just fascinating to see how it has evolved, really, isn't it?
It is an old technology, and
Yeah.
it's funny how 20 years ago everyone thought they really were on the way out, that no one would ever build a synchronous condenser ever again because they were thought to be completely superseded, because we had electronics to deal with the voltage control problems that they were originally used for. But the thing of a synchronous condenser is it's basically sitting there as a rotating machine, as a source of mechanical inertia that just doesn't have a prime mover. So we're using that machine-based technology, but not as part of the energy source, but just as a stabilizing mechanism for the grid and as a strengthening mechanism. So it's not the only solution that we can use, but it's one that is it is based in traditional practice. And as we make this transition and get comfortable with the new ideas around operating the grid as an electronic appliance, these older solutions based on rotating machinery still provide a degree of confidence in being able to move forward while we solve the problems of this century.
And so, Tony, if you had to give one primary piece of advice to those developers or investors, wanting to avoid system strength issues when supplying renewable energy as a power source, what would that primary piece of advice be?
I would be advising everyone to first of all to have good experts on your side that understand the system, that are used to working with those who are responsible for operating the system and ultimately are accountable for keeping the lights on, and ensure that there is there's a process that can be worked through to the satisfaction of all parties, and that we have a rigorous justification for all of the measures we're putting in, and in particular where there's a need to incur additional costs. There's a level of expertise and experience that provides the best possible justification for incurring that cost, because ultimately there's these projects need to be developed with a reasonable cost base to ensure that we fulfil the fundamental market objective we have in Australia, which is reducing everyone's electricity bills. And we've seen costs come down with renewable energy, but to keep them coming down, we have to be using the best technology available. We have to be bringing the best minds to bear on these problems. And speaking more widely, we need to ensure that the next generation of young engineers is appropriately trained to understand these problems as well, and that consultancies like ours at Vysus can actually draw on an ongoing talent base that allows us to find the best and most cost-effective solutions to problems for the whole industry.
All really essential facets. Well, thank you so much for the fantastic chat today, Tony. It's been incredibly informative. How can people connect with you if they would like to find out more information, ask you some more questions, or find out a bit more about Vysus Group and the services that they can offer?
Yes, thank you, Natalie. And I'd say my mailbox is open. You can send an email to tony.morton@vysusgroup.com. We're very happy to answer your questions and solve your problems.
Fantastic. Thanks, Tony. I love that open invitation. Your mailbox is always open. It's very inviting. Well, thank you so much again for being a part of Motion Talks. We really appreciate your time today.
All right. Thank you, Natalie.